Alright, so apparently I needed to quit talking so much. I'll make this fast, okay? So we've got granite number 1, slate number 2, pegmatite number 3, sandstone number 4. Limestone comes from the bottom of the ocean. Remember, it went from muddy terrestrial area to a sandy beach to a deep ocean. Yeah, maybe not that deep, but ocean at least, not beach, okay? This was under an ocean, okay? That's where limestone comes from. And then we have some more volcanic activity happening in the area. We've got this granite magma chamber. Okay, this was a magma chamber that cooled and solidified into granite. You've got the pegmatite intrusive igneous lava tube. Okay, you got the basalt lava tube. And then, oh, I guess that's where I was going with that. You've got the basalt lava tube. More volcanic activity happening here. Basalt is intrusive igneous. This is another lava tube coming up. Maybe this erupted. Maybe it did, maybe it didn't. We don't know. But what we know is that it worked its way through the limestone. We can't know what happened here because that erosion, that surface has been eroded. So this was underwater. Maybe this was a seafloor volcano called a seafloor mount. The volcano underwater. Maybe this was part, attached to an island that was built up over millions of years, and then was creating, you know, uh, volcanic rock, up on the surface. Um, anyway, we don't know what happened because there's another erosional surface here. We don't know exactly what happened here. But in our fictional scenario, remember we went from slate, so this would be mudstone, swampy area, to sandstone beach, to limestone out in the middle of the ocean. There was a big erosional surface here. This was exposed on the surface where weathering and erosion could take place. This could have been underwater. We don't know. For my scenario here, I'm going to say it was on land. Maybe the water level began to drop and drop rapidly, which would have led to all of this erosion happening. Okay, it washed away whatever the rock record was on top of the limestone. Whatever this basalt, whatever happened with this basalt, was washed away. Okay, and then we have volcanic ash. I don't think it would have been this one because there's no evidence of an eruption here. But there's been a lot of volcanic activity happening in the area with the granite, the pegmatite, and the basalt. Somewhere in the same area, there was a volcanic eruption depositing volcanic ash, which solidified into rock on top of the limestone, on top of this erosion surface, on top of this basalt. Solidified into rock. And then on top of that came shale and siltstones, which are terrestrial mudstone type rocks. Okay, again, maybe a swamp, maybe lake beds, river beds, things like that. And then over time, we've got a river here cutting away into the shale and siltstone, causing this valley. Now, the scenario that I just made, the whole thing that I just made it up as I went. I don't know for sure. First of all, this is a fictional place, but if we wanted to know for sure, we would have to do what crime scene investigators do. They go collect more evidence. I've put together one possible scenario, but if we wanted to know if this was really a beach, or maybe instead of a beach, maybe this was an arid desert like the Sahara. In my scenario, I said it was a beach. The way to find out would be to go here and look. Okay, look and see what happened. Look in the limestone. See what types of fossils are here. Look in the volcanic ash. See if there's any evidence left over on this erosional surface that might tell us what happened. See if there's any evidence on this erosional surface, or on this erosional surface, or if there's any fossils in this slate. We can go and look in the shale and siltstone and see what's there to help us get a better idea of what happened. My scenario is pretty generic and pretty open, and probably was wrong. If this was a real place, I probably have a couple of mistakes in here. The way to check would be to go find more evidence. Right? So crime scene investigators do this, geologists do this, and then go find more stuff to come up with a better story. Okay, that's what it's all about. Alright, sorry, I had to stop the video there for just a second. Okay, so my next slide that I have, you don't need to write this stuff down. Let me hit present here. Here we have How do we know about rock layers, and what do we know about, or how can we use this data to come up with information? Well, stratigraphy. When I get back into class, I'll tell you a story. I've got a poster in my classroom. I did stratigraphy work. I got paid to go do it, and that's what really ignited or reignited my passion for paleontology and dinosaurs. I'll tell you the whole story when I come back in person. I've got pictures and stuff that'll go along with it. But stratigraphy is my personal biggest contribution to geology so far, to the field of geology. And it is the study of rock layers. Rock layers are called strata, so the study of rock layers is called stratigraphy. It's a type of geology. Okay? And stratigraphy is all about figuring out the age of rocks. In some cases, we can find out a numerical age, figuring out how many years old it is, how many millions of years or thousands of years. The big one here is radiometric dating. I know I'm going way out of order, but you don't have to write this stuff down anyway. The big one here is radiometric dating. Okay, radiometric dating tells you it's using the ratio of particles within the rocks to figure out how old they are. For example, uranium, fairly unstable, will naturally over time convert to lead. It will change into lead naturally. It will decay into lead naturally. So by looking at the ratio of uranium to lead in rocks, we can figure out a date pretty accurately. Carbon dating is also the same thing. You look at different forms of carbon. Carbon 12, I believe. I don't know a whole lot about carbon dating, but I think it's carbon 12 into carbon 14. Anyway, different types of carbon. It will naturally decay, and we can look at the ratios between them to figure out a number of years. It's very steady, predictable, reliable. Okay. Some less reliable ways are to look at tree rings, dendrochronology, counting tree rings. Okay, it's not an exact science, but it's pretty good, and there is a reason that the bigger layer or the wider layers are wider and the thinner layers are thinner, and that has to do with the amount of nutrients, the amount of water, the amount of sun that is available at the time. In the summer, trees here in Kansas get a lot of sun, get a lot of water, get a lot of nutrients. They grow faster. They get big rings. In the winter, they don't get as much sun. They don't get as much nutrients. They don't get as much water, and so they grow much less, creating small rings. Big ring, small ring. Big ring, small ring. And by counting the number of rings, you can count how old the tree is. Well, that doesn't help us with rocks, but with petrified wood, I have examples. I'll show you when I get back into class. I have examples in my classroom of petrified wood that you can count the rings. Figure out how old that tree was. Now, that doesn't tell us how long ago the tree was alive, but gives us evidence. Okay, varve. A varve is the same kind of thing, except for instead of counting tree rings, it's counting layers of mud at the bottom of lakes and ponds. Okay, the summer you get a thick layer, and the winter when it's frozen, well, less stuff is getting in there, less stuff is settling in to create thin layers. So you have thick layer, thin layer, thick layer, thin layer. You got a thick layer of summer, a thin layer of winter, thick layer of summer, thin layer of winter. Okay. So you can count the varves as well. That's maybe a little more useful in terms of rock. But really, radiometric dating is the way to go. Up here, there's something called relative age dating. No, this is not what happens down in Arkansas. I'm talking about relative age dating. Dating rocks relative to one another. Okay? Using the principles of geology to say that one rock layer is older than the other, or one rock layer is younger than the other, or two rock layers are the same age. The difference between relative age dating and numerical age dating is right here, and this is important. Relative age dating cannot tell you how old the rock is in numbers of years. Look at this right here. We know that the granite is the oldest and the shale and the siltstone is the youngest. We know that. How old is the granite? No idea. How old is the limestone? No clue. How old is the shale and siltstone? Not the slightest idea. We can't tell. There's no way to tell. All we know is that the limestone is older than the sandstone. The sandstone is older than the pegmatite. The pegmatite is older than this. I'm sorry. Whew. I'm going the other. Wait a minute. Limestone is younger than the sandstone. I was saying it backwards. My bad. Limestone is younger than the sandstone. Sandstone is younger than the pegmatite. Pegmatite is younger than the slate, and the slate is younger than the granite. We don't know numbers of years. Okay, that's where numerical age dating comes in. So what I have on the next couple slides are some examples. Look at this, pause it if you need to, and just on the side of your notes, write down the order in which they were deposited. This one's really easy, right? Okay, the answer is A. A is the oldest. B is the next oldest. C, and then D. This one's pretty simple. A, B, C, D. That's the order that they were deposited in. We can tell that using the principles of geology. This next one might be a little more challenging. Pause it and see if you can do it real quick. Just write it on a scratch piece of paper. Write it off the side of your notes. Just see if you can do it. All right. A was here first, right? It's on the bottom. B was deposited, and look, this is unusual. B does not follow the principles of geology. B is an example of an exception. It was originally deposited horizontally, but it's been bent. It's no longer horizontal. B and C were bent through plate tectonics, okay? Through immense amounts of pressure bending the rock. It happens sometimes. It's weird. It's rare, but it does happen. Okay, so A is the oldest, B, then C, and then look, D was deposited and it filled it in like we would expect it to, because D was deposited after B and C were bent. And then you have, or maybe not, maybe D, you can't see any layers here, but maybe D has layers like this as well. I don't know. But D was after C. And then this was all I wrote down. E was deposited, and then F. Okay. We're going to stop here. You don't need to know this stuff. This was for, well, you might want to know it. In all of these different diagrams, limestone is made of blocky, sandstone is made of dots, granite's made with these little squiggly lines, shale and siltstones, mudstones have either dashed and dotted lines or just lines across. You can see here are some of the different shapes that are made, and these are standard. These are industry standard. All geologists will draw limestone as blocks. All geologists will draw sandstone as dots. There are different types of limestone. Okay, so yeah, there's different ones. Shale is shown in gray. Conglomerates are shown blocky. But these are all pretty uniform across the field of geology. You might need this in your assignment today. Your assignment today will be to go, I'm going to exit out of this. I've got a couple minutes left. Okay, your assignment is going to go to geology, to the geology folder, and open up this Principles of Geology worksheet. Okay, it's called the Principles of Geology worksheet. It's on Schoology. It's in the gray folder. I'm sorry, the black folder. It's there. Okay, there are some practice problems. Okay, this is worth 30 points. So you're going to turn this in to me. What you're going to do is you're just going to go through here and do exactly what we've done. I'll work through the first one with you. Okay, the first one is this top one. I'm going to give you the answer, so pay attention. We're going to figure out which one is the youngest and which one is the oldest. I'm going to start on the bottom because it's easier for me to start on the bottom. Okay, so C goes down here at the bottom. This one would be C. Okay? C is the oldest. After C, what comes next? Well, E is on top of C. E goes next. All right, and then after E comes D. D would be next. And after D, whoa, wait a minute. Now we have a problem. D, after D would not be B because A cuts through C, cuts through E, cuts through D, but doesn't cut through B. So the next one would be A. And the youngest one on top would be B. Okay? There's the answer to the first part. Now, the second part, try to determine the geologic history of the area. Well, this is where you get to make it up, and you can be as exciting or fun as you want to be. I guess as boring as you want to be. I don't really care. But I want you to attempt to come up with what happened. So C, if you want to be really fancy, you can go back and look at the notes and see what type of rock it is, although you don't have to. I'm just going to say C was deposited with E coming after, I don't know, and then D is the sandstone. Wow, this is, yeah, you can kind of see what I'm doing. D follows the limestone, I believe that's basalt. I'd have to go back and look. Oh, I'm running out of time. Okay, so then I'd say the dike cuts through C through D be